that although these are force problems, or more importantly, these are Newton's law questions, what we will produce by the end of one of these sessions isn't an answer to any question. The hope is that what you produce by the end of this will answer any question that is given of you. But a force problem can only be, when I say a force problem, when you apply Newton's laws to a problem, all you will actually be able to figure out is an individual sized force or perhaps an acceleration. But there might be something that is also evident in the answer that's beyond just what's being asked. Now, I'm going to employ this procedure, but understand the procedure doesn't require a question. You're simply analyzing a circumstance. And in the analysis of that circumstance, you're coming to some conclusions that Newton's laws can provide. Now, an actual question, problem that you'd be given will have something with a question mark, something it will want you to find out. And hopefully by the end, whatever you produce from Newton's laws will be able to answer that question. The procedure is the same regardless. I'm training you on the procedure. I really don't care about the questions. So we will follow this procedure each time. Now, I want to be honest. This procedure is not adept at certain types of problems. For example, the car accelerates at 2 meters per second squared. The car has a mass of 1,500 kilograms. What net force acts on the car? That's not what I'm about to do. This is a plug and chug physical science question. It is not what Newton's laws are about. Yes, you will be asked these kinds of ridiculous questions. Yes, they show up in the homework in textbooks, and they show up on multiple choice questions. This is not a Newton's law problem. This is a plug and chug kind of problem, and it hinges on the idea that there is a net force. This does not tell you anything about what's really happening in nature, and therefore is a ridiculous question. But yes, this could be the kind of question you get. I am not teaching you how to do this. Okay, I'm afraid that if you can't figure out what you were supposed to do here, then we are in more difficult circumstances. And I think you understand why we're not teaching this. This is not what's really going to be asked of you. Yes, it is true that the net force must have been 3,000 newtons, but who knows what other forces were actually happening in addition to what was happening with the car. So here's what I more of the situation you should be preparing for. We're going to call this the sign problem. And to give it a little context, here's what my imagination is. I want you to imagine that you are in a strip mall where there's like a curb usually. So cars are parked like here. And there's maybe a door here. It's a doorknob and an awning where the roof is. Imagine a sign being hung in such a way that you could see the sign as you walked under the awning. Can you guys imagine this kind of arrangement? Does it make sense? A little bit? Whether it does or not, this is what I'm imagining, even though that picture is terrible. So let's get a more zoomed in picture of the sign, because all I care about is the sign. And in your notes, this reason I choose this example is because A, it is a static example, and we should all start with at least one static example. And B, it really does a good job of identifying ways in which trig and coordinate systems need to be used. So here's our zoomed in problem. I have the sign, which is the box. The box is mass M. It is attached in such a way that there are two cables connected to it. One of them is perfectly horizontal. The other one acts at an angle of theta with the horizontal. There is tension in both cables. The question is, what is the tension in each cable in terms of the weight of the object? That's the question. Now, regardless of what the question is actually asking, the procedure we're going to employ is the same every time when dealing with a Newton's law problem. So, to begin this problem, I want you to remember that the series of steps applies to every force problem that's out there. It will work every single time in analyzing any circumstance. It is the more complicated way of analyzing a circumstance. But believe it or not, there is no other way to do this problem. There's no other simplification. This is the only way to do this particular problem, is by using this series of steps. So, step one, and when doing your notes, what I would encourage is maybe have the side of your notes set up so that you can give kind of comments on what you did in each step. Because although these are the things I want you to do, there's clearly things that are missing from this list that will need to be done. The nuance, what it means when I say to make decisions or apply. So I'm going to start with the first step, which is to kind of decide whether you think this is a first law problem or a second law problem. It will guide many of the decisions we make from here on out. The object is not moving, but that's not the thing that decides whether it's first or second. What decides is if it's accelerating or not. I need to bring that up because if it's moving, that doesn't immediately mean it's a second law problem. You have to ask yourself if the object is accelerating or not. This object is not accelerating. That makes this a first law problem. So I'm going to start the problem by reminding myself this is a first law problem. The forces should appear to be balanced. The next step is for us to go through and identify the forces that act on the object by drawing a free body diagram. I am incredibly mean about the free body diagram. It has to be done in a precise way. And on the test, I will have an area of your test set aside just to judge your free body diagram. I am going to be judging the neatness of your diagram. I will be looking at the length of the arrows you draw, the direction of the arrows that you draw, and the way in which you label the arrows. Those are all things that will be looked at for judgment. So please be aware all of those are things that I am focused on when you guys are drawing a free body diagram. First, you should know that a free body diagram takes any object with mass and reduces it to a point. So if you have more than one object, you will have more than one diagram. Now, we're only dealing with the single body problem, so all of ours for right now are just going to be a single diagram. But when we start talking about multi-body diagrams, you'll have multiple diagrams that will have to support the problem. Now, when drawing the free body diagram, it is incumbent upon you to know that the free body diagram is an instrument that is used to solve these problems. If this instrument is done incorrectly, you will be unable to solve these problems. So part of the reason I'm hard on you about getting these right is once we draw this diagram, not only is it something that will be graded on a test, but then you will go forwards with this diagram and use it to solve your problem. So I need them to be accurate. Now, really drawing a free body diagram is just drawing a whole bunch of arrows that start at the dot. And each arrow represents one of the forces acting on the object. You have a collection of forces to which there are certain reasons why you would choose one over another, but you apply their definition to your object and decide whether they are indeed acting on the object. For example, you should ask yourself, is there any fundamental force acting on the object? And the first answer here should be yes. Gravity is acting on the object, so you should begin with a downwards arrow. It's hard to find a problem where gravity isn't acting on the object. Now, the drawing of the first vector for weight sets the scale for the rest. So when drawing this arrow, be aware of the future of what this problem should look like, because the other arrows are being drawn in such a way as to kind of respect the proportions of the problem. And if you don't understand what I'm trying to say by that, I have to draw another arrow now. And I'm going to ask myself first, is the object in contact with any surface where there is a normal force acting on the object? And I see no surface in contact with the sign. So there is no normal force acting on the object. Go to my next force. Is there any cable or rope acting on the object? Answer is yes, there are two. There are two cables attached to the object. Now, which one should I draw first? And it might not be obvious why you should draw cable 1 first. But cable 1 is the only thing that appears to be pulling upwards on the object. Do you notice that? So I'm going to draw cable 1 first because the only thing I know about the object currently is that it's being pulled down by gravity. So since cable 1 is the only thing pulling up on it, then I want to draw cable 1 in such a way that it appears to be large enough so that the upward portion of cable 1 balances the downward portion of weight. So I'm trying to draw cable 1 proportionally to the scale of the problem. I'm being guided by the fact that for every up there should be a down, and for every left there should be a right, because the forces are balanced. That's what Newton's first law suggests. So I've drawn an arrow here. I'm going to label it T1 to represent the tension in the first cable. Now I have some information I can use about drawing T2, because T2 is there to balance out the fact that the first cable is pulling to the left on the object. So cable 2 must be pulling to the right on the object. It's not arbitrary. It needs to be pulling in such a way that the amount that T1 pulls to the left is balanced by the amount that T2 pulls to the right. So, go to my next force, friction. Do I believe friction is acting on the object? Well, no, I don't. Friction can only act if there's a normal force, and there's no normal force here. So you should be clear to not worry about friction if there's no normal force, because friction is caused by a normal force. The last one is drag, or air resistance. And air resistance can only be acting on the object if the object is moving. Our object is not moving, so there's no air resistance. At this point, we've made it to the end of the list. And unless somebody or the problem states that there's another force acting in the system, you're done drawing your free body diagram. That's what you should be getting when you're done with the free body diagram. A collection of arrows, all appearing to start from the dot itself, and are all being drawn away from the dot. If you're being graded on your free body diagram, you should stop here. Now, we need to draw on a free body diagram to do the rest of the problem. On a test, there will be an area for you to draw your free body diagram, but if you need to do work on it, you will need to draw another one that you can do work on. But this is just a practice problem, so we're going to do work on this one specifically. But again, on a test, it is very likely you will have to do something here afterwards, and that process should be done on a separate diagram, not the one that's being turned in to be graded. Does everybody understand? And I'll make that clear on a test. But the next part of this is for us to actually use this diagram to solve the problem. And if we look at our list here, the next thing we're going to be doing is applying a coordinate system. The application of a coordinate system is a delicate matter, and there are two priorities to which you should kind of adhere strongly. The first priority is the one that you should always do first if possible, and that is to draw your coordinate system in such a way that it is aligned with the acceleration of the problem. This object's not accelerating, so I don't think that priority is going to help me out very much here. The second priority is to align your coordinate system with as many forces as possible. Now, in previous years, students kind of just assume then that they can draw their coordinate system however they wish. And when I say that, I mean that they might say that, well, the y-axis is, I'm going to make the y-axis, let's see, there. I'll make the y-axis this way and the x-axis this way. No, you can't do that. It's a coordinate system, so the two axes must be perpendicular to each other. But that doesn't mean you should say, okay, then I'm going to make the x-axis like this and the y-axis like that. I mean, you could. The truth is, This choice of a coordinate system is 100% your decision. But our next step is that any forces that are not along an axis will require trig. So if I do it this way, I'm effectively making sure that I have to do trig for all three of the forces here. Now, unless you just have some desire for punishment, your goal should always be to try and line up as many forces as possible with your axes to reduce the trig that is necessary. It's clear to me that these two forces are at a right angle to each other, therefore would line up with a coordinate system. So I'm going to line up my axes with those two forces. I could line them up with tension 1, but that doesn't seem like the right way to go. If I line them up with tension 2, then it means it's automatically lined up with weight. So I'm choosing a coordinate system that is lined up with T2 and weight because they are already at a right angle to each other. Now, in choosing a coordinate system, you are also identifying what direction you will call positive. This is not arbitrary. This is necessary. So you'll notice when I draw a coordinate system in, I almost always identify a positive direction on each coordinate system. You should do so too. Now, what's not up here, which should be step C on applying a coordinate system, is that any off-axis forces have to be converted to components that are aligned with your coordinate system. Any off-axis forces have to be broken up into components that are aligned with your coordinate system. So I'm going to transfer the angle here because the angle is aligned with the horizontal. And I'm going to recognize that to convert this into components, I'm going to wrap a triangle around the angle. Now, I'm kind of done labeling opposite and adjacent sides now. I want you to get to a point where you can just say this is T1 cosine theta, because it's the adjacent side. And this one is T1 sine theta, because it's the opposite side. You may not be there. You may still have to do sine equals opposite over hypotenuse and kind of draw it all in. That will take more time. But I'm also hoping that you're beginning to reach a point where you recognize why the trig works the way it does. Cosine and sine are percentages. It's a number between 0 and 1. It's a percentage. So we're trying to figure out how much of T1 is in the x direction. So this tells us the percentage of T1 in the x direction. And how much of T1 is in the y direction is given to us by sine. That's what this is about. Now, once you've done this, the truth is the actual vector no longer is necessary in the picture. We are replacing it with our two components. Effectively, what doing this is actually allowing us to consider is that our problem has now been broken up into two one-dimensional problems. We have weight down and T1 sine theta up, and we have T2 to the right and T1 cosine theta to the left. The truth is, breaking up our T1 into components means we don't need to look at T1 anymore. That these are the actual forces acting in this system. All right, so that takes us all the way down to the last step. Are there any questions yet? Excellent. So the last step says to apply Newton's law. Now we already chose the law that we're going to apply, that net force equals 0. But now you have to kind of extend this. We can only do one-dimensional math, which means that this actually translates into net force in the x direction equals 0 and net force in the y direction equals 0. If the net force equals 0, then a net force equals 0 in all directions. Now, if our system was accelerating, then one of those will probably be ma. But we're not quite there yet. Now, here's where I remind you that Newton's laws are not equations. They're instructions. And the instruction here says to add up all the forces in the x direction, taking into account their direction, and set them equal to 0. It's a set of instructions. So in order to obey those instructions, I'm going to go find the forces that are in the x direction. I'm going to take into account the fact that one is positive and one is negative. I'm going to sum them and set them equal to 0. That's what my set of instructions tells me to do. And I'm going to do that for every dimension that I've carved out in the problem. Our problems will only be two-dimensional, but our job is to carve them all out. So this is the result of applying Newton's law in the x direction. In the same way that in the y direction, I'm going to add up all the forces in the y direction, taking into account their direction, and set them equal to 0, which means T1 sine theta minus weight equals 0. That's it. That's how you use Newton's laws. At the end, it doesn't tell you the answer. It gives you 2 or 3 custom relationships that might be able to be used to answer your question. But Newton's laws themselves don't tell you anything else. They just form these relationships. They tell you how the forces in your system are interrelated. And this is how the forces in our system are interrelated. Now, you might be able to solve your problem with this. You might not. And when I say that, I don't mean that Newton's laws might work or might not. I mean, you might not have the mental capacity at 2 p.m. on a Monday to use this to solve your problem. You might never have the mental capacity. And some of you might have it, but not really know what I'm expecting here. But you were asked to figure out the size of the tension in terms of the weight. I don't think this one's going to do that for you, because weight isn't in here. I do think this one might tell you something, because weight is in here. Seems to me I could at least get one of the tensions in terms of the weight. So that's what we'll do now. One of the tensions in terms of the weight. Let's solve that for T1. I'm going to get weight divided by sine of theta. Now, a lot of students really balk at this, and I don't really know why. I need you to kind of be here and present for this. T1 is almost always going to be greater than the weight, is what this tells me. Right? Sine of theta is almost always a number that is less than 1. So regardless of what I'm going to hang, it is very likely that the cables I'm going to use are going to have to be stronger than the weight of the object. If I buy cables that are just able to hold the weight of the object, I'm probably going to be disappointed. Because unless theta is 90 degrees, then the tension's always going to be greater than the weight. That's what this equation tells me. It tells me something important. It tells me when I'm going to buy the supplies, I better buy the right kind of cable. You might think that's silly, but there's enough funniest home videos of people trying to sit down or swing on a rope and the rope can't support them. And people think it's because somehow, that the rope was too weak for their weight. That's not true. You can buy a rope that's able to hold the weight of the sign and still won't work. Because this says that most of the time the tension is greater than the weight. Interestingly enough, too, it tells me that there's no way I can support the sign if cable 1 is horizontal. Do you see why that's true? People paying attention, I hope, do. Because if I try to put in 0 degrees here, I have a problem with math, don't I? Can't divide by 0, although some of you in your lab thought you could. But you can't divide by 0. And sine of 0 is 0, so there's no way the cable can be perfectly horizontal. But look at your picture. That shouldn't surprise you. The only way the object has static equilibrium is if there's an upward force to balance a downward force. If cable 1 is perfectly horizontal, what's pulling up on the object? So there's got to be some amount of force upwards if you want to balance a downwards force. Now we're not done. You're supposed to get both tensions in terms of the weight. And it seems to me, now that I know T1, I could probably use that to figure out T2. In fact, that's exactly what I think we should do next. So we should substitute. So where I see T1, I'll put W sine theta times cosine theta. Except I hate that. You should not leave it like that. You guys who are novices to physics, you might also be novices to the fact that this is cotangent, cosine divided by sine. But I like that even less because I hate cotangent. I hate secant and cosecant. That just seems like a cop-out. I think we should write this as weight divided by tangent theta. Because cotangent is 1 over tangent. Now, I found out earlier today that there are quite a few people who don't know that this is true. And I don't know who you are, and I don't want to know now. But sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So sine over cosine is opposite over hypotenuse divided by adjacent over hypotenuse. If I multiply this by hypotenuse over hypotenuse, I get opposite over adjacent, which is tangent. Which is why sine theta over cosine theta is tangent theta. So if you didn't know that, now you know. And I don't need to know that you didn't know that. All right, so we are actually done now. We found our two relationships. I expect that you can get the relationships to look like this with the amount of mathematics that you have, meaning I expect you to be able to do this little bit of trig. But most importantly, I expect that you can follow this process, which in this case gave us expressions for the tensions in terms of the weight. Now, if this was AP Physics 1, we'd be putting numbers in there and they'd be getting just like the values. They wouldn't have gone this route. In this class, expressions are important. And I expect you to be able to understand why the expressions are important because they tell us things about the nature of the problem. Like you might not see this, but if you use 45 degrees as your angle, T2 will be equal to the weight. Right? Tangent of 45 is 1. So if you choose this angle to be 45 degrees, then the cable that's attached to the wall pulls with as much force as the weight of the object does downwards. You better make sure you choose the right kind of mount for the wall, or you might pull it out of the wall. People really don't have any idea how this stuff works. You should, especially if you're going to hang like a shelf in your house. It might be appropriate. All right, so we have gone through to use this process on what I feel is a very straightforward question. I chose this question more importantly to ensure that you guys could see the process, less importantly for you to feel like you know how to hang signs. But with each of these examples, I'm trying to add something more to the problem. So we won't have time to do to completion, but you should give it a shot this evening. And be prepared to discuss it tomorrow. This is example 2, the elevator problem. And I am amazed at how often people follow the elevator problem all the way through to the end without any difficulty. And then when they're asked themselves to do it, can't. I don't know why that's an issue, but it always seems to be the case. So here's the elevator problem. And this problem comes in many different forms, but if you've ever been on an elevator, then you probably note that the elevator accelerates upwards to get up to speed first. The elevator is nothing more than a box with a string connected to it. You may be in the elevator, but it starts from rest, accelerates upwards, and then gets to its cruising speed. When it's at its cruising speed, it's no longer accelerating, it's moving at a constant speed. People inside, happy, going about their business, elevator moving upwards. But then when it gets to the floor that you've selected, it has to accelerate again, but this time it has to accelerate downwards. It's moving upwards, it needs to slow to rest, so it has to accelerate downwards in order for it to stop. There's many ways that this problem is set up. Some of them ask about the person in the elevator. Some of them ask about the elevator itself. We're going to do this problem from the standpoint of the tension in the cable and its effect on the elevator. We're going to say that the elevator accelerates upwards at 2 meters per second squared. Yes, I'm going to give you numbers to use. And it accelerates until it reaches its cruising speed of, who cares, 1 meter per second. It's at its cruising speed, it goes upwards at 1 meter per second until it reaches the floor, where it's going to stop and accelerates downwards at 3 meters per second squared to come to rest. Let's say you plus the elevator have a combined mass of 500 kilograms. The elevator problem will ask, what is the tension in the cable for each segment of your journey? Okay. Apparently I have a wireless caller. That's what my caller ID says. No name, just wireless caller. Glad that they are a wireless caller. All right, so that's the question that you have to answer. Unfortunately, there's only 1 minute left, so this is where we're going to start. You should attempt part of this problem. I don't care which part, but trust me, students get this problem wrong all the time, especially on multiple choice tests. So give it a shot. I'll tell you this, the answer is not 1,000 newtons, ever.